All right, so I think it's time to kick off this great webinar. Welcome everybody. Good morning, good afternoon, good evening. I guess you have joined for different parts of the globe, and we are quite excited for that. So I'm really happy to welcome to this webinar Professor Qinru from the Electrical Engineering Department at the University of Syracuse, right? So allow me to say a few words about her CV, and then I'll give the speech to her. So Professor Chiu, she received her PhD in electrical engineering from the University of Southern California in 2001. She's been a professor with the Department of Electrical Engineering and Computer Science at Syracuse University. She has been working in the areas of machine intelligence and neuromorphic computer for the past 20 and 15 years, respectively. She has been awarded several awards, like an NSF Career Award back in 2009, the IEEE Region 1 Technological Innovation Award, and she has been also an ACM Distinguished Member since 2022. She also offers editorial service in several IEEE transaction journals, such as the Neural Network and Learning Systems, the Selection System Magazine, the Transactions on Cognitive and Developmental Systems, and so on. She's also served as a member of several technical program committees for various conferences, some of which are sponsored by IEEE CEDA, such as DAC, ICCAD, DATE, and so on. She's the director of the NSF and UCRC ASIC Center Syracuse site. And very, very recently, and we are all excited about this because she is also a member of IEEE CEDA, she was elevated to IEEE Fellow. So warm congratulations for that again, Qinru, for this great achievement. And with this short introduction, I will pass the floor to you and enjoy the talk.
Thank you, Dr. Pavlidis. Hello, everyone. I'm very glad to have this opportunity to talk about neuromorphic computing on the IEEE Education Week and also introduce some of our recent works. So this is the outline of my talk. I will talk about basically first give the introduction and the motivations of why we want to study neuromorphic computing. And then I will introduce some of the computational neural models and information coding schemes and the computing hardware platform, and followed by the learning algorithms. Finally, I will give a case study and then we'll provide some conclusions. So why we're interested in neuromorphic computing? Basically, we want to learn from human brain for its energy efficiency. We know that IT information technology has increasingly amount of energy dissipation over the last decade. In 2022, the data centers consumes more than like 460 terawatt hour of energy. That's enough to power 1/3 of homes in US. And this number could rise to 1,000 terawatt hour by 2026. And much of this power is used to provide energy for AI servers. For example, AI server could use between 85 to 134 terawatt hour energy annually by 2027. To give some specific example, training a GPT-3 requires about 1,300 megawatt hour, and to perform a query of GPT-4 consumes about 1 to up to 10 watt hour of energy. And as a comparison, an iPhone 15 has only battery capacity of about 12 watt hours. So on the other hand, human brain is very energy efficient compared with conventional computers. A GPU card may consume more than 250 watt of power. However, the human brain, excuse me, the human brain has only about 20 watt of power consumption, but it is more capable in terms of cognitive applications. And one of the reasons that conventional computer is inefficient in terms of energy is because of memory wall. So in the von Neumann architecture, we know that the CPU and the memory are separated. The fast CPU and slow memory actually create a memory wall. The figure I'm showing here actually shows that over the last 20 years, the computing performance of hardware, the hardware computing performance increases more than 60,000 of times. However, the bandwidth of DRAM increases only about 100 times. And to make things worse, the bandwidth for the off-chip interconnect actually increases only 30 times about. So the very fast CPU and slow memory and even slower off-chip interconnect actually prevent the performance of the computing system. And also it increases energy dissipation. For example, to perform a 32-bit addition operation consumes only 0.1 picojoule. However, to read a 32-bit data from DRAM consumes more than 600 picojoule, which is almost 200 times more than performing a floating point multiplication. The human brain performance actually acts differently. If we consider neurons and the transistors both as computing elements, then the human brain and a conventional computer has about the same number of processing elements. However, each neuron in the brain has up to 1,000 or up to 10,000 of connections, while a transistor in a conventional computer has only no more than 10 fan-out. The human brain operates a very slow frequency compared with conventional computer, and each neuron is not as reliable as a transistor. However, when they're putting together, the entire system is very reliable and very energy efficient. So people have estimated that even with the most advanced computer nowadays, we probably cannot reach the intelligence of a mouse. If we try to build a computer using conventional architecture and software to achieve the intelligence of a human brain, we need a lot more memory and computing power, which will consume a lot more energy. So exactly how human brain can achieve such high energy efficiency is mostly a mystery. However, there are already some observations from neuroscience that can provide part of the explanations. For example, we know that the brain has massively parallel architecture, and the memory, which is stored in synapses, are basically massively distributed and closely integrated with computing elements. And moreover, all the neurons operate in an event-driven manner, and the communication is using spikes. So a little bit about biology. So each neuron has a cell body, which is called soma, and one output called axon. And it has multiple inputs, which is called dendrites. The axon actually forks out to connect with inputs. The connection point is called the synapses. So the membrane potential of the neuron performs something like leaky integration of its input. And the ion charge of sodium diffuse into the cell to increase the potential, and the ion charge of potassium leaks from the cell to reduce the potential. And when the membrane potential builds up to reach a threshold, a spike is generated as output, and the potential is then reset. So the neuron communicate with each other with event-triggered and asynchronous spikes. The synapse, which is the connection between input and output, actually opens and closes the ion channels by releasing the neurotransmitter. And in this way, it facilitates the inter-neuron communication with variable efficacy. And the recent study shows that each input actually acts like a leaky integrated filter. So the entire neuron itself is a network of big filter. And in this way, it can be used to detect temporal patterns. And when a lot of these neurons connect together, then they form a spiky neural network. So let's talk about the computation model of neurons. over the last decade, there are many computation models has developed. They have different accuracy and complexity. And as usual, we know that the model with highest accuracy usually accompanies with high complexity, and vice versa. So there are two extremes models we will introduce. One is the Hodgkin-Huxley model. The other is leaky integrate model. And they basically on the two extreme end of the spectrum. Based on how neurons' behavior is described, they can be divided into ODE model and SRM-based model. The ODE model basically describes neuron behavior using a set of ordinary differential equations. And they can further be divided into conductance-based model and spike-based model. The conductance-based model represents cell behavior using an equivalent RC circuit. For example, in the Hodgkin-Huxley model or HH model, the membrane potential is represented by the voltage across a capacitor. And we also use a variable conductor to represent the potassium ion channel. There's another variable conductor to model the sodium ion channel. And there's another conductor to represent the leakage channel. So overall, the relationship between current, voltage, and conductance follows a set of differential equations. So as we can see, this model is quite complicated. And the input basically is considered as the injected current. And both the input and voltage are real numbers. And this type of model gives the highest accuracy, but highest complexity too. So they're used widely only in the computational neuroscience. On the other hand, the spike-based model abstracts the input and output as a set of spiking activities. Each spike is represented using the direct delta function with an offset TF, which indicates the time of the spiking activity. And a sequence of spiking activity basically is a summation of all the direct delta function. Similar to the conductance-based model, the voltage and the current relationship is described by a differential equation. And the output is calculated using the membrane potential and the threshold voltage using a Heaviside activation function. The Heaviside activation function basically says when the membrane potential is greater than the threshold, the output is 1, otherwise it's 0. So as we can see that the spike-based model simplified the entire behavior so that the output and input of the neuron are binary, either 0 or 1. Because of its simplicity, so it is widely used in machine intelligence. The spike response model describes neuron and dendrite dynamics using their impulse responses. Basically, this model considers each dendrite as a filter. The filter has kernel K. There are different types of filter, like exponential kernel, alpha exponential kernel, and a dual exponential kernel. So basically, the kernel is described using the impulse response of the filter. When a set of input spikes goes through the filter, and it generates something we call post-synaptic potential, or PSP. The PSP obviously can be calculated as the convolution of the input and the filter kernel. Similarly, the output spike also goes through a reset filter, and with the kernel R. And finally, the membrane potential is calculated as the summation of all the post-synaptic potential scaled by some weight coefficient and minus the reset. And the output, again, is calculated using the Heaviside activation function. So we can see that the SRM-based model is more complicated than the previous leaky integrate leaf neuron, leaky integrate, and fire neuron. However, it's also considered a very simplified abstract level of input and output. And we know that the filters can be represented using digital infinite impulse response filters. And a general form of an IIR filter is like this. Its output can be represented as P stages of forward taps. with coefficient alpha, plus Q stages of feedback taps with coefficient beta. So if we draw this structure to replace the synapse, right, and also the reset filter, we can see that the neuron actually is a recurrent network. It has a lot of recurrency. So each neuron actually is a recurrent neural network. So this is another way to represent the behavior of a neuron. So about the information encoding. So in a spiky neural network or in neuromorphic computing, the information is represented using spiking activities. There are in general two types of encoding scheme, rate coding and temporal coding. The rate coding represents a value using the rate of spikes. And a high spiking activity represents a larger value and vice versa. So this type of coding scheme is widely used in spiky neural networks. However, it has some limitations. First of all, it will have long observation latency, because in order to evaluate the spiking rate accurately, we have to collect enough number of spikes in order to basically minimize the sampling error and to minimize the rounding error. However, the typical neuron firing rate is very low. It's from about 1 Hertz to 200 Hertz. So to wait to collect a large number of spikes probably will need several seconds, which will cause long latency. And also it will cause a lot of spiking activities, which again will increase the power consumption. So there has been some evidence from neuroscience research showing that rate coding probably is not what the biological system does, or at least it is not the only encoding scheme used by biological system. For example, a fly can respond to a visual object only after receiving 1 or 2 spikes. So there's obviously not enough sample to accurately assess the spiking rate. So that's why people also using temporal coding. Again, there are different types of temporal coding. There's latency coding, or also called time to first spike coding. It encodes information in the latency of the first spike. There's also phase coding. Basically, it represents the information by relative spike timing with the respect of a periodical background oscillation. So I need to point out that how exactly brain encode information is not yet fully understood. So different neural coding may coexist in the same system. For example, in the picture here, I showed how the neuron activities are received when to encode an external pinch on the finger. Depend on the type of pinch, and it depends on the size of the receptive field, and also depend on the intensity of the pinch. The spiking activity is different. Obviously, they cannot be explained only using rate coding or temporal coding. So basically, for a neuromorphic computing system, it is important to be able to adapt to different type of input coding instead of assume a specific coding scheme. In our work, we use something called Cuba neuron or current-based leaf neuron to encode the input stimulus. So the input basically, so when the input has high intensity, this Cuba neuron will output the spike at high spiking rate. And when the input has low intensity, the spiking rate will be lower. So as we can see, it achieves adaptive spiking rate. So it's kind of combination of rate coding and temporal coding. We also find that it is not efficient if we only encode one channel of sensor information using one neuron. Actually, it is better if we use multiple neurons to jointly encode multiple input channels. And we call this temporal population coding. So this actually gives an example of how we utilize the temporal coding. So in this example, we collect the sensor reading from a data glove. The window in the upper left corner actually shows the sensor readings. We use this reading to classify different hand gesture. Each gesture has 500 samples if we want to use digital signal processing to process them. If we try to convert each of these data sample using the rate coding, then we will have a lot of spiking activities and a lot of input channels. However, if we use the Cuba neuron to encode and population coding, then we will have very sparse spiking activity. Actually, we can reduce more than 90% of spiking activities. And utilize these encoded spiking activities, we can accurately classify the different type of hand gesture. So about neuromorphic hardware, there are different types of neuromorphic hardwares. In general, they can be categorized into supercomputer-based platform and ASIC-based platform and analog and mixed signal-based platform. An example of supercomputer-based platform is SpinMaker. It is a massively parallel computer built on ARM processors. It has about 1,200 boards, up to 1,200 boards. Each board is a 48-node array. Each node is a multi-core chip with 18 ARM cores. And each ARM core actually is relatively simpler. It has only 32 kilobyte instruction and 64 kilobyte data memory. And an example of ASIC platform is Tianji, which is a 28 nanometer reconfigurable chip, which support both ANN and SNN. So this chip has about 156 cores, and each core has 32 weights and 250 fan-in and fan-out. An example for the analog and mixed signal system is BrainScale S. This is a multi-core system with analog computing and digital communication. So the system has 20 neuromorphic wafers, and each wafer basically has 56 radicals. Each radical has 8 analog chips, and each analog chip can be used to implement 128 synapses and 512 membrane potential circuits. So this analog chip can be programmed to implement the conductance-based neural model, as we explained before. Another widely used or widely known ASIC neuromorphic hardware is Intel Loihi. There are 2 generations of Loihi. The Loihi 1 is implemented using 14 nanometer process, and Loihi 2 is implemented using Intel 4 nanometer technology. So the Loihi 1 basically can be used to implement up to 128K neurons and 128 million synapses. The chip actually follows a 2D mesh network of 8 by 16 cores. And the on-chip communication bandwidth is 8 gigabyte per hop per second. And each chip on the Loihi processor has 128 kilobyte synapse memory, and they can be used to implement up to 1,024 neurons. And each neuron actually has a programmable learning engine. So this programmable learning engine allows us to update the synapse weight in order to achieve in-hardware learning. And there's some additional features in Loihi 2. For example, the Loihi 2 now support graded spikes. So the spike is no longer 0 or 1, but has levels. And it also supports microcode programmable neuron. So with this neuron model and neuromorphic hardware, we would like to implement a neuromorphic system that is capable to learn, right, to implement certain functions. There again are different learning algorithms. First is the SNDP learning algorithm, which is widely accepted to be the most biological plausible learning rules. It's believed that the biological neuron actually follows this learning rule. The rule is very simple. If we have 2 neurons connected, we have a presynaptic neuron and a postsynaptic neuron. again, the presynaptic neuron actually sends the input, and the postsynaptic neuron actually generates the output. If the presynaptic spike, or in other words, the input, is immediately followed by a postsynaptic spike, in other words, an output, then we say that these two neurons has a causal relationship. Then their interconnect must be strengthened. And on the other side, if the postsynaptic spike is immediately followed with a presynaptic spike, then these two neurons is considered to have an acausal relationship. Then their interconnects will be weakened. So basically, as we can see, this rule is very simple and it's basically unsupervised. So we can use STDP learning to train an unsupervised feature extraction layer. For example, given 100 neurons, if we keep exposing this neuron to the MNIST image, right, then they eventually will learn some features as shown in this figure. So these are some like general patterns of the MNIST digits. However, if we want to train a classifier, then we cannot use it. We use the STDP learning. Some modifications have to be adopted. So we basically add a teacher neuron and add a winner-takes-all structure at the last layer, at the classification layer, in order to train a classifier. So the teacher neuron will try to activate one of the output neuron that's corresponding to the target class. So then this activation will make this output neuron fire a lot of output spikes, which will again suppress all the other output neurons through this winner-takes-all structure. In this way, in the output layer, only one neuron is spiking. And at the same time, this neuron also receives input from these feature neurons. So the input spike and output spike will have very high correlation. Based on the STDP rule, this output neuron, the target output neuron, will gradually strengthen the connection to these features that try to excite, connect to it, or corresponding to the correct pattern. So at the end of the training, when all the output neuron has learned the connection between the feature neurons, then we will take away the teacher neuron. So now with only the excitation from the feature neurons, the output neuron can be excited correctly. So as we can see that we can use STDP learning to train a classifier. However, this kind of training can only happen in the last layer. The supervision of the teacher neuron only applies to the last layer. We have no way to propagate it to the feature extraction layer or to the layers before it. And in order to perform supervised training to train other classifiers, we need a way to backpropagate error signals. So in our previous work, we developed a learning algorithm called Error-Modulated STDP, or EMSTDP. So the idea is quite simple. We construct two networks. One is feed-forward network, one is feedback network. The feed-forward network will propagate the signal to generate the inference result, and the feedback network will propagate error backward. And then, instead of considering the only each single output spike, we consider the relationship between the total input spike and the total output spike. So this relationship basically follows this staircase function. And we approximate the staircase function using a shifted ReLU. And following the general backpropagation learning, we know that the delta W, the weight change, is a function related to the derivative of the activation function and upper level gradient, the input, and the upper level weight coefficient. So because we have already approximated the activation function using the shifted ReLU, its derivative is either a constant or zero, depending on whether the accumulated membrane potential is greater than the threshold or not. And then we need a way, because both the feedback and the feed-forward network are implemented on neuromorphic hardware. So, using the LIF neuron, leaky integrated fire neuron, and so the gradient or the error needs to be also represented using spike trains. Then we know that the error has positive and a negative error. So we need a dual rail. Basically, we need dual rail or two rails of spike trains to represent both positive and a negative error. And at the same time, so basically, the feedback neurons will get error from upper level and multiply with the weight coefficient, and then to calculate the weight of current level. And the weight calculated will then be forwarded to the feed-forward neuron to adjust, basically, and basically this error will adjust the membrane potential of the feed-forward neuron, so that this feed-forward neuron has changed the behavior. Its output activity rate changes. So if we use H hat to denote the spiking activity before change, before the error correction, and we use H to indicate the spiking activity after the error correction, the difference of these two actually is proportional to the error. So in this way, actually each feed-forward neuron has all the components, needed component to calculate the delta W. It has the error, it has the input rate, right? So they can, basically, we can calculate the delta W using the backpropagation rule. However, again, the EMSTDP has a limitation. It assumes that the input signal is encoded using rate coding. That's why we only consider the relationship of total spiking rate between the input and output. So if we want to train a network to detect temporal encoded input, then we need to consider the temporal dynamics, which is the filter effect of neurons. And as we mentioned before, if we use IIR filter to replace the synapse filter and reset filter, we actually get a recurrent neural network. And then we can use conventional backpropagation through time to train this recurrent neural network as general. This is what we do in general. And how the BPTT works is it tries to unroll the recurrent neural network over the time. So in this figure, each vertical slice is a copy of the network, but at a different time. This is the first slice at t-1, and at the second slice at time t, the third slice at t+1. So when the signal enters this network, it propagates from bottom to top, which is from the input layer to the output layer. At the same time, it propagates from left to right, from an older time to a more recent time. And then with this network, we just apply conventional backpropagation to train each connections. And so the gradient error propagation basically will propagate from the top right corner to the bottom left corner. So as we can see now, the BPTT actually is quite complicated. First of all, we need to unroll the network, and we need to memorize all the neuron activities over the history. If the input sequence is long, we will need a lot of memory. And also, secondly, we need to wait until the entire input sequence has propagated through the entire network, which means every input value needs to propagate from the bottom left corner to the top right corner and leave the system. Then we can start to backpropagate. And then the backpropagated error again has to be propagated from the top right corner to the bottom left corner. So basically, it involves a lot of latency and computation. So again, the fourth type of learning algorithm is called three-factor Hebbian learning. The Hebbian learning is, again, something similar to STDP learning. It's very simple. It says neurons that fire together will wire together. And the three-factor Hebbian learning assumes that each neuron maintains an eligibility trace. And this trace will capture the input and the output spiking activities over the history. And based on the three-factor Hebbian learning, the weight update is determined by the reward modulated with the eligibility trace. For example, it can be written in this way. It's the delta weight is the summation of mu and summation of the product between mu and epsilon. The mu is a reward. It could be an error backpropagated from the output, or it could be external reward. And the eligibility trace epsilon basically is a combined record of input and output spiking activities. For example, it can be the leaky integration of input and leaky integration of the output, which is calculated in using this equation. So basically, we very briefly introduced the 4 different learning algorithms. And of course, there's another learning algorithm, which is the very brute force effort. We first train an ANN using backpropagation, then we convert it to SNN. So in this table, I try to compare those different learning algorithms for their accuracy, for the flexibility, whether they can handle both rate coding or temporal coded input, and based on whether they support online learning or whether they support implementation on neuromorphic hardware, and whether they support supervised learning or unsupervised learning, and also how much resource they will need. So I try to basically rank them. As you can see, they have pros and cons each. And at the end, at the last row, I give some basically examples or representative works for each learning algorithm. So next, I want to talk a little bit about a case study of how we implement EMSTDP learning on Loihi. So the Loihi basically supports programmable learning engine. As long as you can write your weight update rule in this equation, it can be supported by the hardware. And in this equation, W is the previous weight and W prime is the updated weight. S is the coefficient. And the most important thing is probably the V. V is basically a trace. As we mentioned, an eligibility trace could be a leaky integration, right, of either the input spiking activity or the output spiking activity. By programming the leaking or the decay factor of the filter, we can control we can have many different eligibility traces. For example, we can have just the raw input and output spiking activity, or we can have the average total spiking count of the input and output, etc. So in our implementation, we constructed 2 networks, as we mentioned, one feed-forward network and one feedback network. And both inference and learning are taken place in the feed-forward network, and the feedback network only used to backpropagate errors. And we adopt a 2-phase operation. In the first phase, which is the free response phase, the input propagated through the feed-forward network, and the inference result is generated. And during this time, the neuron collects the output activity, H hat. And then in the second phase, the error backpropagated through the feedback network. At the same time, the input still propagates through the feed-forward network. And the error is sent to the feed-forward neurons to adjust its activity. And during this phase, the neuron collects the spiking output activity at H. And then based on the difference of H and H hat, and also the input activity, the neuron calculates delta W. And all these variables, H hat and H, can be collected using the traces provided by the Loihi programmable learning engine. But then in order to implement this into hardware, there are some hardware limitations we need to consider. First of all, the Loihi hardware synapse weight has only 8-bit, so the maximum weight is limited to 255. However, we would like our error spike to have very large weight because our feedback phase or error correction phase is small. The neuron can only receive only 1 or 2 error spikes, and we would like the error spike to be able to affect the neuron behavior. So they must have large weight. So we have to duplicate the error spike. There are 2 ways to duplicate the error spike. We can either duplicate them temporally or duplicate them spatially. So for temporal duplication, we use one intermediate neuron. When it receives an error spike, it will duplicate it into multiple spikes over time. In spatial duplication, each feedback neuron is connecting to multiple intermediate neurons. And this intermediate neuron will forward the error spike to the same feed-forward neuron. In this way, the spike is duplicated. But then obviously, which solution you want to choose depends on which one is more important, whether it's latency or it's the hardware resource. They represent different trade-offs between these two. And the second thing we need to consider is the I/O bandwidth of the chip. So as we mentioned, the EMSTDP encodes the input using rate coding. So each pixel in the MNIST image is encoded as a sequence of spike trains, the spiking rate corresponding to the pixel value. But obviously, we can see that we will introduce a lot of input activities to the Loihi chip, which is not desirable because it has large energy dissipation. Therefore, what we did is we introduced an input layer. Each neuron in this input layer is a stochastic neuron. And the bias of those stochastic neurons is programmed to be the pixel value of the corresponding image of the image pixels. And the stochastic neuron then will generate output spike randomly. The probability of the output spike is proportional to its bias, which is again proportional to the pixel value. So in this way, we basically reduced the I/O activities and therefore also reduced the energy dissipation. And after we construct the network, the next step is to map the neurons to each course in the each neuromorphic course in the Loihi. And this can be done using the Lava tool provided by Intel. So this slides basically give some experimental results. We tested the in-hardware learning using different data sets from MNIST to Fashion MNIST to M-STAR, which is this radar image, and to the CIFAR-10. And we compared the Loihi training with Python-based training algorithm. The difference of Loihi implementation and Python implementation is that the software implementation has floating point weight coefficients. However, the Loihi-based implementation has only 8-bit fixed point weight coefficients. And we can see that the two gives about the same accuracy in terms of training and testing. And we also try to compare the performance, power, and energy among the CPU, GPU, and the 2 generations of Loihi processors. And the first column gives the frames per second, which is the indication of the performance. So, and we tested for both training and testing. So we can see that the Loihi implementation has much higher energy efficiency than CPU and GPU implementation. So actually, as the conclusion, there's some basically takeaway points. So first of all, the biological neural system has remarkable energy efficiency. and it provides a lot of inspirations for neuromorphic computing systems. And while computational neuroscience usually use models with a lot of biochemical details, machine intelligence usually favors to simpler and more abstract level models. And in a neuromorphic system, information is encoded in different ways. And the decision of encoding scheme and the learning and inference algorithms and hardware implementation styles are closely correlated. So that you cannot pick one and ignore others. You need to make this decision together. And also, most of the neuromorphic computing is targeting at adaptive sensor and actuator applications. So it's important for the neuromorphic system to be able to support online learning. And also it is important for the inference and the learning to be able to implement on the same hardware fabric. In this way, basically, it will be most cost and energy efficient. So with this, basically, I conclude my talk, and I'm ready for to take any questions.
Great, thank you very much, Qinru. So the floor is open to questions. I don't know if you have used. Cannot see any on the Q&A. I don't know if there are any on the chat. Laura, can you help us if there are any? You have received any questions yourself?
I'm not seeing any questions at the moment.
Right. Okay. So let me just ask one question. Maybe more people will encourage to jump in. Qinru, in your opinion, I understand, and you pointed out very clearly that the different encoding schemes that we use for SNNs make a significant difference on the requirements for I/O and also for energy consumption, etc., etc. How far do you think we are from the 20 watts that our brain consumes? You know, how do you think that is feasible to reach close to these, levels of energy consumption for performing, some, I would say, not, very simple decisions, but something more elaborate like our brain can do,
Mm-hmm. Yeah, so I personally, I think to achieve 20 watt probably is challenging, but we could do much better than conventional or current computers. This is because I think most of the computation, unless we probably can perform similarly, like using biochemical process or other computation mechanisms to do computing, right? It probably will be difficult. And another reason is the brain actually is the product of millions, or I don't know, actually many years of evolution. So the structure also is important, probably. But I think that the key here is we want to learn from it this kind of either structure and behavior, the entire mechanism of computing to improve current computer. And it's not to replicate the brain.
I see. Thank you. Anyone who may want to ask anything or comment?
I see there's a question from Ian. Could you explain better how is performed the supervised learning in the output layer? The teacher, I did not understand what exactly is the teacher neuron. Okay.
I think you had a slide where you had a teacher neuron, yeah? I guess that's the question about that slide. Yes.
Yes. So let me go back to this page. So the teacher neuron basically will activate the correct output neuron. That's its function. So basically teacher neuron, it's like the neuron knows the answer. So we will have, if we have 10 classes, then we will have 10 teachers. And then the teacher will, the teacher corresponding to the correct class will be activated, and then it will highly excite the corresponding student or output neuron. So the function of the teacher neuron is basically to excite the correct output neuron. And when the output neuron is excited, it will generate output. And so that in this way, we will find the correlation between the input spike and output spike. And in this way, the connection between the student neuron and the feature neuron will be strengthened. I hope this answers your question.
Right, let me see if there is anything else. Right, so as Laura pointed out, and I think you wrote it on the chat window, that this lecture will be posted on IEEE CEDA site, but there is also some time for another question, so feel free to write if you have any, to type it in. Okay, thank you, Leo, for your warm round of applause. We can see it in the window. Right, so yes, in that case, I think we can close this talk. Thank you. I would like again to thank Professor Chiu for her very interesting talk. I loved your slides very much, and I will definitely download them when they're available on our website. And stay tuned for the next 10 upcoming webinars. And see you soon in the next one. Qinru, thank you very much again.
Thank you.
Yeah.
Bye-bye.
Bye-bye.